Good morning, everyone. Welcome to this morning's a16z crypto research seminar. Very happy to introduce Justin Thaler, who, as you know, just showed up this week as a faculty fellow. He'll be with us for the rest of the summer, which is very exciting. Justin's a professor at Georgetown, and today he's going to give the first of his two-part tutorial series on snarks. So just a couple reminders. So the second part will be Tuesday at the same time at 11 a.m. And then actually in the meantime, later today at 2 p.m. we'll have Scott commenters as well as a seminar. Okay, so Justin, all yours.
Thanks a lot. So I'm going to tell you a little bit about SNARK Design, well, what snarks even are, how they're built, and how they're used in rollup projects, which are pretty exciting right now as they're being built for blockchain scalability. Today will be not super technical. Tuesday, Tim said I could just go crazy, so. Okay, so what is a snark? So in a snark, some untrusted prover claims to know some witness satisfying some property. So a couple examples that come up a lot in cryptography. So the prover might claim to know a pre-image W of some designated output of a hash function. Right? So here the witness would be a W such that h of W equals Y, where sort of the prover and verifier have agreed in advance on the hash function h and the output y. And the prover is claiming to know W, and the verifier doesn't know W and wants to make sure the prover does. Another example, which is related but not quite the same, is the witness might be a private key corresponding to some known public key for some crypto system. Okay, so there's always a trivial proof for the prover's claim, which is to just send the witness W that it claims to know to the verifier. Then the verifier can just check that W satisfies the claim property. For example, in the first bullet point here, the verifier could just evaluate the hash function at W and confirm it equals Y. Okay, so what a snark does is achieve the same goal, but with hopefully much better cost for the verifier. So this is a funny acronym. It stands for Succinct Non-Interactive Argument of Knowledge. So let me tell you what each of these letters mean. So succinct means that the snark proof must be shorter than the witness W. Right? So there's like a trivial proof, it's just the witness. So anything that's shorter than that, I'm going to call succinct. In the research literature, some authors will reserve it to mean like logarithmic in W or even smaller than that. I just think anything non-trivial should be considered succinct. Ideally, checking the proof should be faster than the runtime of the verifier in the trivial proof system. That's not actually captured by a letter in the word in the acronym SNARK. So if I have to clarify that issue, we'll call it a work-saving snark, like the verifier saving work compared to the trivial proof system. Could be you have a short proof that takes a lot of time to check, right? But that wouldn't be work-saving. Okay, the other letters, so non-interactive means the proof is static. It can be posted on a website or sent in an email. And then argument of knowledge just basically means if the prover can't break some crypto system, then it really must know W in order if it's going to produce a convincing proof. That's, yeah.
Is there like some notion succinctness is short relative to the size of the statement too? Because it seems like for the hash pre-image, like the snark is never going to be shorter than the witness.
It can be. It can be.
I mean, what if the hash pre-image is 80 bits?
Sorry, that's shorter than the. Okay, so yeah, there's like an asymptotic question versus a concrete question. There are snarks with like non-negligible sound. Sorry, with non-negligible soundness error that might be shorter than 80 bits. In principle, anyway, I think that's possible. Anyway, in practice, you're not going to get a snark proof that's smaller than several hundred bits. So if your witness is that short, in practice, you're not going to be more succinct than that. But there are statements that could have larger witnesses. The prover is proving to know many witnesses, many pre-images or something. Yeah. So in practice, there is a limit to succinctness. The most succinct snarks, it's 3 cryptographic group elements. So you're talking, what is that, like 600, 800 bits? I forget.
And so just for concrete issue, we'll be thinking about shorter and faster, just like logarithmic the witness length, or what would you recommend?
Yeah, so we'll get into issues like transparent snarks and not transparent snarks. There are non-transparent snarks where short really means like 3 group elements in a cryptographic group. That's like 600, 800 bits, I think. If you want a transparent snark, you're probably not going to do better these days than logarithmic in the statement size or something. Logarithmic in something. Okay. And then, yeah, so, and I'll say more about what fast means. Like you can hope for a few milliseconds for these non-transparent things when the proofs are really short, and tens or hundreds of milliseconds for the transparent things, I think, for the verification. Yeah. Okay, and something I just mentioned, the rollup application does not require zero knowledge. If you don't care about privacy, you just care about blockchain scalability, you don't need zero knowledge. So I will not call them ZK rollups. I think it's a bit of a misnomer. I will call them validity rollups today, if I have to clarify what kind of rollup I mean. Okay, so here's the plan for today. First, I'm going to tell you about how are snarks designed. Then I will give you sort of a taxonomy of existing snark constructions and their pros and cons, and that'll give you, really it boils down to right now like 4 classes of snarks out there today that people are using or might use soon. So kind of you can fit it all in one slide and understand how they relate to each other. And after that, we'll turn to rollups. I'll tell you what is a rollup, how they're using snarks. And there won't be time today, I don't think, but if there is more time, I'll start the slightly more technical overview. So if parts 1 and 2 do feel a little bit technical or just dry because you don't care about cryptography, just come back for part 3. You won't need to know parts 1 and 2 for part 3. So how are snarks designed? At a high level, most snarks work via a 2-step paradigm. So ideally, you would start with something like a computer program written in a high-level language, and that computer program is just going to take the witness that the prover claims to know as input and check that the witness satisfies the property claimed by the prover. So in like this hash preimage example from earlier where the prover claims to know a preimage under a cryptographic hash of some hash output, the program would just evaluate the hash on the witness and check if it equals the claimed value. So like applying like a snark directly to a computer program, like conceptually, like can't really be done. So the first step of this 2-step process is to transform that computer program into an equivalent model that is amenable to probabilistic proof systems. And typically this is some kind of circuit satisfiability instance or some kind of generalization of this. Some people like something called R1CS. It's a generalization of circuit satisfiability. You don't have to worry about the details. There's a movement now to go sort of beyond even more intricate things, even beyond R1CS. But this transformation from the program to something like a circuit is that's called the front end of the system. And then you would apply a snark for circuit satisfiability to the circuit. That's called the back end. So all of these like snark names out there in the literature, which maybe you've encountered some of them before, they refer to the back ends, the probabilistic proof system, where the prover is now sort of claiming to know a satisfying assignment to a circuit instead of like a witness, that a preimage of a hash value or something. And they're equivalent claims, right? The front end is ensuring that the circuit sat instance is equivalent to, the original computer program, essentially. It's just circuits are kind of like a lower level language, if you will, than C or Java, kind of. Does that make sense?
One question. So in step 1, you talk about turning into an equivalent model amenable to probabilistic checking.
Mm-hmm.
And so I'm wondering if you can say something about like why, right? And you never talked about probabilistic checking before. You said the goal is just succinctness.
Mm-hmm.
So I suspect what's going on is succinctness will come. There'll be a particular way that the succinct proofs will mean something like a bunch of probabilistic checks, and that's why you wrote that in step 1.
Yeah, that's right. That's right. So what's happening in these proof systems, in these snarks, is conceptually the verifier is sort of randomly challenging the prover, but then the randomness and any interaction is completely pulled out of the protocol using cryptography and kind of replaced with sort of the keys of a crypto. The randomness is kind of replaced with the keys of a crypto system, if you will. And in that way, you wind up with a static proof where the verifier never has to send a challenge to the prover or anything. So yeah, this.
Is it fair to say, like, in principle, you could imagine any number of approaches to what a succinct proof may represent, but like the dominant paradigm is what it represents as the results of a bunch of random challenges. Given that that's the dominant approach, we shouldn't be surprised to see that step one means you need to basically re-prepare the same program in a way that you can check it through random challenges.
That's exact. Yeah, you said everything much better than I did, so I won't try to repeat it. Yeah. Yeah.
Cool.
I would just like, because I'm thinking about the difficulty of step one versus step two is like reducing having like general program to like the circuit representation, like relatively easy compared to step two, or like how's that?
So easy and hard might not be the right wording. It's the question is also the overheads. Like, you know, if the program runs for 100 steps, but the circuit has 1 billion gates, like that's not great. But also if the circuit has 1 billion gates and sort of the prover's runtime is, you know, equivalent to evaluating a circuit with, you know, 100 trillion gates, that's also not so good. So there's going to be overhead in both steps. You know, some computer programs are much more amenable to being turned into small circuits than others. You know, asymptotically speaking, we sort of have both steps close to the best we can hope for, which is, you know, up to like log factors in either step. We kind of, you know, can't hope to do any better, but concretely those log factors matter and the constants matter and everything in practice, these can be quite nasty. Yeah. But no, the infrastructure itself, kind of building it and even understanding it, maybe that's what you mean by difficulty, can be quite challenging. Like, you know, if you don't care about really squeezing as much overhead out as you possibly can, making these as performative as possible, there are fairly straightforward ways to kind of do both steps. I mean, even the simplest things for step two use some of the most celebrated ideas in theoretical computer science. But if you really want these things to perform, everything is kind of challenging to understand the details of and to make sure it's bug-free and all of that. They just get complicated. Does that answer the question?
So, there's another way. So you're basically saying, step one, it should be intuitive that, like, yes, we should be able to do something like that. That's kind of conceptually, I don't want to say straightforward, but, you know, we're used to kind of different levels of computation simulating each other. Whereas step two, it's not clear a priori that should be possible.
Correct. Yeah, and I would say, to unpack step one just a little bit, you know, the world's kind of dumbest program-to-circuit transformations would yield. It wouldn't turn into a. How do I want to say that?
So you mean like Cook's theorem or something?
Yeah, like Cook's theorem. Like your laptop is really built out of a circuit, right? But there's this question of, is it circuit satisfiability or circuit evaluation? And you run into this issue where the prover is claiming to know a witness, the verifier doesn't know, so there's kind of non-determinism already built into the problem itself. But the really efficient transformations from programs to circuits, they will add more. They will like extend the witness with advice inputs that help keep the circuit small. This is actually, you know, I have a sort of book and I have a reading group, and this is one of the concepts that's sort of hardest to describe verbally. Is like the circuit satisfiability instance, the witness to the circuit is actually the witness in the prover's head with extra stuff in it to help the compilation from programs to circuits. So yeah, you know, SNARK programming is something like the practitioners refer to, and they're talking about how you put in these extra advice inputs to the circuit to keep the circuit small. And yeah, so even like relatively straightforward things here are going to use those advice inputs, and hence it's a different way of thinking than Cook's theorem might be, say, a little bit. So I hope that color is a little helpful. Most of this talk is on back ends, but I will talk about front ends because in the rollup context, you know, the overheads at both steps are really important. Pictorially though, you know, here's the picture, right? Is a computer program gets turned into some kind of circuit sat instance, and then the prover and verifier, you know, they both sort of know the circuit somehow, and they apply a SNARK for the prover to establish it knows a satisfying assignment to this circuit. The last thing I'll say is the front ends that people are using, that a lot of, you know, the front ends, the idea that they would start with like a C or Java program is purely aspirational. Like people aren't really doing that in practice. Many people are writing in very low-level languages, such as like Bellman and what else do they use? CircCom. They're almost just writing out the circuit gate by gate. Okay, and then other approaches will have something slightly higher level than that, but it's still like an assembly-like language. And so obtaining front ends that really would take an arbitrary C program and spit out some circuit sat instance that's not just horrible is really not. It's still an open problem, I would say. So just some extra color there about where we are, and yeah, what the programmers are really going to be writing if they want to use these snarks. Okay, so with all that said, yeah, my main focus and my main expertise really is on the back ends. So our back end goals are we want a snark for circuit satisfiability, where the prover is not much slower than just what it would take to evaluate the circuit gate by gate on the witness, like with no guarantee of correctness. So that's sort of the best you can hope for, is like prover has to at least convince himself that the witness satisfies the circuit, right? So we want the proof to be as small as possible. So yeah, the smallest but non-transparent snarks will be a few hundred bytes, or it turns out if you want a sort of a nice version of non-transparency, there'll be half a kilobyte to a few kilobytes. Actually, even the transparent ones, we can get down to a few kilobytes. And we want the verifier to be fast as possible. Again, from a few milliseconds is sort of the fastest we have now to maybe 10 times that or something. There are other properties we would want beyond just fast prover and fast verifier. So now we get to, I've been saying this word transparent, I haven't told you what that means. And I will say in just a second, the other thing we would ideally like is for the snark to be post-quantum secure, meaning if the prover has a quantum computer and is trying to find convincing proofs of false statements, it still can't do it. Okay, so what does transparency mean? So in a non-transparent snark, the prover will have to know what's called a structured reference string. So this is a very long string. They'll call it a proving key in practice. Typically, it's as big as the circuit. Okay, so it's big. And there'll be a trapdoor such that if the prover knew the trapdoor, it could easily find convincing proofs of false statements. Okay. So like to generate the SRS, like kind of someone will have to know the trapdoor. SRS is structured reference string. And you'll have to sort of trust that party to then forget the toxic waste, dispose of the toxic waste. So what people do now, there's been a lot of really nice work to sort of minimize the trust assumption. People will run like a giant secure multi-party computation protocol, hundreds of participants, and unless they're all getting together and colluding, no one knows the toxic waste. So kind of as a trust assumption, it's fairly minimal now, but as a headache and something you don't want to have to do over and over again, it's still, it's a giant pain, right? So I'll say more about how various snarks differ in terms of the kind of trusted setup they require. But yeah, if a snark is transparent, it means you just don't have to worry about that at all. There is no trusted setup. There's no trapdoor that someone might know and could forge proofs of false statements if they knew it.
So sometimes I hear about these distinctions between setups that are circuit specific versus.
That's exactly what I was getting at.
So you'll get into that. Okay.
I'll get into that more later. Yeah. So, but the point, but I can say now, like you don't want to have to run a different trusted setup for every time you tweak your circuit, or ideally you'd like 200 people get together, run the trusted setup, and forever in the future, anyone, doesn't matter what circuit they care about, they can use the same SRS as long as their circuit isn't too big. And that's kind of what people are doing today. Like Zcash and others ran some of these trusted setups a while back, and now other projects get to use those same strings as long as they believe that someone in that ceremony from long ago, people call these ceremonies, was honest and didn't collude with every other person in the ceremony. I see there's something in the chat. Should I pull that up?
Sure.
Okay. Best simple. Oh, okay. Good. Thank you. Someone liked the definition of a snark. So.
Oh yeah.
Okay. Good.
It's actually one other question. So I wonder if it would be helpful to. We keep talking about these circuits in the abstract, which in some sense we're all used to, but looking ahead toward rollups, especially sort of discarding the privacy aspect of if there's a canonical circuit. Let's say for validity rollups built on Ethereum. Should I think of it as taking as input like a state root and a bunch of Merkle proofs and a transaction, and then sort of also then the alleged consequent state root, and I'm just checking that that's legit, or?
That's exactly it, yeah.
Okay.
Yeah, and I'll say more about that later. But and then for the simpler example of just a hash preimage, right? The circuit would literally just like evaluate SHA-3 on the input. That's it.
Thought about like the transparency issue, and I guess like how much do you think it's a real issue in practice with all the like multi-party setups and stuff versus like a branding issue in the cryptocurrency space?
Yeah, I think my personal feeling right now, which sort of evolves over time and probably will continue to, is that the biggest downside of the trusted setup is it limits the size of the circuit you can deal with. And if we, ever want to apply these snarks in blockchain applications, the statements being proven tend to be very simple in like a cosmic sense. Like you could imagine using snarks in other contexts where the statements are vastly more complicated. Circuits would have to have trillions or more of gates. You're not going to run a trusted setup for that. And there are techniques you can use to try to mitigate this, like recursive composition, which I'll say a little bit about. But that's what I feel. I'll say more about where trusted setup has been like a thorn in people's sides if I have time later in the talk. I'm not so worried about the trust assumption. I think if 200 people get together, that they're not all employed by the same person or something, they're probably not colluding. Last thing I'll say, there have been bugs in like Zcash. The Zcash bug was they included extra stuff in the SRS that shouldn't have been there, and that would have let people potentially create Zcash out of thin air, sort of something like that. So just maybe that means that the complicated nature of these snarks with an SRS. I don't want to draw too strong a conclusion from that, but it was an SRS issue that led to that bug.
So just to connect some dots there, you said your main concern about trusted setups is limiting the circuit size you can handle. So is that because you said that the reference string needs to be basically order or size of the circuit, and then the point is just like people actually carrying out the MPC, just realistically it was only so long on?
Yeah, exactly. And it's got to be distributed to anyone in the world who wants to operate as the prover, which in the blockchain setting could potentially be anyone in the world. Yeah, so it's just expensive to generate and distribute, and if it's trillions of gates, I mean that thing has to be a trillion cryptographic group elements. You could distribute that to everyone in the world. That doesn't sound like it'll work to me. The verifier, of course, doesn't have to know the whole SRS. It only has to know like a few group elements or something. But yeah, unless you want the prover to have a massive memory machine or something, it's not going to be nice. And every single person in the MPC to have the same memory. That's my take. It could continue to evolve.
So does that mean, so like for the circuit we just discussed about validity of sort of a state transition in Ethereum, I mean, it almost feels like you're saying like it's sort of inconceivable you'd have a non-transparent, like that you'd have something with a trusted setup that could handle that circuit. Is that right? Or?
Oh yeah, I mean, well, people are running rollups now,
right.
and the reason circuits can get big there is because they want to handle a batch of huge number of transactions, and so the circuit's not just doing one state transition plus Merkle authentication paths for like any piece of data access, but rather, hundreds of thousands or something like that. More questions? Cool. Okay, so here we get to sort of the more technical part of today. So if you want to zone out, it's really not going to matter, but maybe you're interested. So here's kind of the main paradigm for developing a snark for circuit satisfiability. This has 3 steps sort of in and of itself. So first you design something called a polynomial IOP. I'll say in a moment what that is. Then you combine that with a cryptographic primitive called a polynomial commitment scheme. I'll say shortly what that is. And the combination of the two will give you a succinct argument, but it'll be interactive. And then you can pull the interaction away and just be left with a static proof by applying something called the Fiat-Shamir transformation, the details of which don't really matter for this talk. Okay. So let me tell you what is a polynomial IOP, but first I'll clarify the statement that all snarks are designed in this three-step paradigm. So that is almost true. There's just like one exception, which happens to apply to the first snarks that were deployed in practice, especially in Zcash was maybe the main initial deployment. So these snarks are based on something called a linear PCP, which while the letters are different is actually fairly close to a polynomial IOP. And in fact, if you look at the crypto that's used to turn the linear PCP into a snark in this class of snarks, it looks very similar to a certain popular polynomial commitment scheme. So I really don't feel like I'm lying to you very much if I just kind of hand wave a bit and say all snarks are designed in this three-step paradigm. It's a slight lie, but not a major lie. Okay. And in particular, these snarks that went into the initial version of Zcash and became very popular and still are, they require a circuit-specific trusted setup. So if you're not happy with that, then you really have no choice but to use this three-step paradigm. So I like this paradigm because you can sort of get a unified view of every snark that's out there, and given how many snarks are out there, that seems like a useful view to have. So okay, so let me say a little more about what is this weird thing called a polynomial IOP. I'm actually only going to describe sort of a special case of that, but it just makes it a little easier to present. So imagine you have a prover and verifier, and they're willing to interact with each other, which means like the prover can send a message to the verifier, and the verifier will respond with a random challenge to the prover, who will respond with some response, and the verifier will send another challenge and get a response, and at the end of the interaction, the verifier is going to like accept the prover's claims as valid or reject them as invalid. So a polynomial IOP is just like that, except the first message in the protocol specifies a polynomial. And I really mean like, in many cases, it's a univariate polynomial. So like a plus bx plus cx squared plus dx cubed, right? A polynomial. Except the polynomial might be really big. It might be as big as the circuit that the prover is making a claim about. So you don't want the prover to actually have to truly send like all of the coefficients of the polynomial to the verifier, because that'd be a huge message, like as big as this. It's not succinct at that point, the protocol. And you certainly don't want the verifier to have to read like all the coefficients of the polynomial, because then it won't be work saving for the verifier. So instead, we're going to tell the verifier, look, like the prover's going to kind of send you this polynomial, but you're not going to be allowed to learn the whole polynomial. All you're going to be allowed to do is like evaluate the polynomial at one point. So that's what a polynomial IOP is you sort of have this initial message that's special. So it's like some giant polynomial, and because it's special, the verifier doesn't learn the whole polynomial. It's only allowed to evaluate the polynomial at a single point. But then like the rest of the protocol is like the interactive proof I just described, where whatever message the prover sends the verifier is going to read the whole thing, respond, the prover is going to send the message, the verifier reads the whole thing. So it's an interactive proof, but where the first message is this weird giant polynomial that the verifier only gets to evaluate at one point. Does that make sense? Any questions about it? So in the real world, right, we don't have a way for the prover to like send a giant polynomial to the verifier and the verifier to evaluate it at one point without like reading the whole thing, right? So that's where cryptography comes in. So a polynomial commitment scheme is just sort of exactly what you want to implement polynomial IOP without the prover like literally sending the whole polynomial to the verifier. So at a high level, it lets the prover bind itself to the giant polynomial by sending just a really short commitment. Typically, this will either be what's called a Merkle hash. It's just one cryptographic hash value, it's a couple hundred bytes or something. Or it will be something like a Pedersen commitment that's just a single element of a cryptographic group. If you don't know what that means, it doesn't matter. The point is, it's just a really small message from the prover to the verifier. The verifier can read that tiny message in full. And sort of once the verifier knows this commitment, you think of the prover as sort of being stuck with whatever polynomial it sort of had in its head. You kind of think of that polynomial as being like shoved inside the commitment, and the commitment is locked, and the prover can no longer alter the polynomial once he sends this locked box to the verifier. Okay, so then later when the verifier chooses the input x that it wants to know h of x, the committed polynomial evaluated at x, the polynomial commitment scheme has to come with a manner in which the prover can provide the evaluation as well as a proof that the evaluation is consistent with the committed polynomial. Okay. And this is just exactly what you want to sort of implement the polynomial IOP without the prover like literally sending the polynomial in full to the verifier.
So the way you described it, the verifier could in principle choose their X as a function of the commitment they see from the prover.
Correct.
I assume that whenever you do this, V is just choosing X randomly independent of the actual commitment. Is that right? Or
Yeah, so in the end, X will just be random,
right.
and the
like reason about what each might be via the commitment, right? I can't do that, right?
if you don't care about zero knowledge, like none of the verifier has no reason to try to read anything into the commitment. Like the protocol, the proof systems will be sound if X is chosen at random. The verifier just wants sound. Soundness means, for anyone who hasn't heard of this, it just means it's a security. It means that if the prover is making a false claim, the prover can't find a proof that convinces the verifier the claim is in fact correct. So the verifier just cares about soundness, so to make sure the prover is not lying. And to guarantee that, it's going to be enough for X to just be random. If you cared about zero knowledge, you're certainly going to have to worry about whether this commitment reveals any information about the witness, and in fact it might if you're not careful. But we won't care about zero knowledge today. Other questions? Okay, so now that you know what a polynomial IOP is and a polynomial commitment, I can give you the taxonomy of snarks. Essentially, there are a bunch of different polynomial IOPs out there. There are a bunch of different polynomial commitments, and you can just mix and match the two with some caveats, but most polynomial IOPs will sort of combine with most polynomial commitments. And any combination of the two gives you a snark with sort of a different cost profile. So costs are sort of inherited both from the polynomial IOP and the polynomial commitment. One thing I'll mention is these properties that are important in practice, whether for practical reasons or branding, for both. Transparency and post-quantum security, they're determined essentially entirely by the polynomial commitment scheme used. So any polynomial IOP could yield a transparent and plausibly post-quantum snark if combined with a transparent and plausibly post-quantum polynomial commitment. Up to some subtleties that's really not worth getting into, certainly not today, of details of quantum security proofs. But if we're just talking about plausible post-quantum security, we really don't even have to worry about those subtleties. So yeah, transparency and post-quantum security, it's all coming from the polynomial commitment, not from the polynomial IOP. Yeah.
So the reason you would mix and match is that the IOPs are doing some operation with the commitment, and then based on their runtime of whatever the IOP is, and then it's making a black box call to this thing that has its own.
Right.
And so that's why it may make sense to mix and match rather than just.
Yeah. So basically, the polynomial IOPs come with a bunch of costs of their own, right? So, the prover is going to, obviously, even ignoring, the prover will have to use a polynomial commitment scheme to commit to some polynomial and later prove an evaluation of it. There's no avoiding that, right? But on top of that, the prover is going to have to, compute the polynomial that needs to be committed and then send other messages to the verifier in the protocol. So sort of outside of the polynomial commitment, there's prover time, there's proof length, messages the prover sends to the verifier, which have to be ultimately in the snark proof. There's the verifier time to check those messages. So the total cost of the final snark is the sum of sort of the cost of the polynomial IOP and the cost of the polynomial commitment. So if your polynomial IOP has big-ish proofs, there's not much point to using a polynomial commitment with really small proofs if it has worse costs on other axes. That's kind of the reason for choice.
Okay, can I still rephrase my question? So all of these things you mean are just sums. They don't interact in a funky way.
No.
Okay.
Yeah, I mean, there's other than subtleties about how some polynomial IOPs can't quite use some polynomial commitments, and that just boils down to the prover in the polynomial IOP sort of wants to represent the polynomial via a certain set of coefficients, and the polynomial commitments might or might not work with those kinds of coefficients, and that's like way in the weeds. We don't have to get into that.
I see, but like for the most part, if for some reason I decide all I care about is prover time, there's a best IOP and there's a best
Yeah.
scheme.
Yeah. But then the desire for transparency and post-quantum security can then change which one you have to use. Yeah. Other questions? Okay, so at a high level, there are kind of three classes of polynomial IOPs. The details I'll maybe say something about on Tuesday, but today it's not really going to matter. It's just sort of you can design a polynomial IOP sort of based on something called interactive proofs, something called multi-prover interactive proofs, and something that I call them constant round polynomial IOPs. And I've roughly listed them just in order of increasing prover costs from top to bottom and decreasing verifier costs. So it sort of makes sense that prover costs and verifier costs are in tension, because if you could if they weren't, then there'd just be something to rule them all. There's something with the best prover and best verifier, and why everyone would just use that. So it tends to be, stuff with the fastest prover has slightly bigger proofs and somewhat slower verifier, and stuff with the fastest verifier has slower prover.
And is there a sense that that tension is fundamental or just sort of an artifact of the current list of construction?
Wait for 2 slides. Okay, and then there are 4 classes of polynomial commitment schemes. I'm going to ignore the last one because it's not practical. I thought, yeah. So let me just focus on the top 3. So the first one is the only one that's not transparent. So it has, this is basically where trusted setups come from in SNARKs. And the most popular variant here is due to KZG. Everyone calls them KZG commitments, Kate et al. And so I've highlighted it in green. So for each category, I've highlighted in green the commitment scheme that sort of right now is sort of the most popular or widely known. And in each case, they have the shortest proofs. And so I think what's happened, the reason the ones in green are so popular is in the blockchain settings. These proofs get stored on chain and they get verified on chain. So people are sort of moving to the extreme of good verification costs. So the ones in green in each category are the ones with the best verifier cost. So there's another category which is transparent, but it's not post-quantum because it's based on the hardness of discrete log, which is a problem quantum computers can solve efficiently. So the most popular one here is probably bullet proofs. Maybe some of you have heard of it. So basically KZG-like evaluation proofs are constant size. That's like 3 group elements or some, not 3. Anyway, some constant number of group elements. Bullet proofs is log number of group elements. And then the last category is both transparent and plausibly post-quantum. And the most popular one here is FRI. Fast Reed Solomon Interactive Oracle Proof, that stands for. And the proof length there is like log squared times the security parameter, or something like that. So I've listed the 3 categories also in sort of, this time in increasing order of proof length. So constant size evaluation proofs, log size, polylog.
Question?
Yeah.
So does that logging what the IOP sends to the commitment scheme, or is that logging the circuit size?
Okay, so in most SNARKs, the polynomial committed to is as big as the circuit, and possibly even bigger by a constant factor, and also some of them you're committing to multiple polynomials, the proof's committing multiple polynomials that are as big as the circuit. There's only one category of SNARKs, and this gets into how there are these trade-offs between prover time and verifier time. Interactive proofs can make the committed polynomial only as big as the witness to the circuit, and not as big as the full circuit. But to support general efficient transformations from computer programs to circuits, the witness will have to have these extra advice inputs, and in general there might be a ton of advice inputs. So you sort of that difference between circuit size and witness size, sort of in general is only a constant factor anyway. But there might be some settings where you don't actually need many advice inputs to have a small circuit, and then these interactive proof things start to look really nice for the prover because it's only committing to a tiny polynomial. And that's why these things are so hard to compare to each other, because you get into interactions between the front end and the back end, and is the witness big or is it small? Does that answer your question?
And also, for post-quantum secure, all that means is that once quantum computers exist, I should no longer use something that's not post-quantum secure. It doesn't mean that once quantum computers exist, there's something insecure about things that already happen.
That's right. So basically, a quantum computer could find a convincing proof of a false statement, but if you're confident no one had that quantum computer when the proof was generated, you don't have to worry about it. Another thing I'll say is, if you do care about zero knowledge for all these snarks, it's the soundness that might be broken by a quantum computer. Zero knowledge is perfect. So the quantum computer will not let you violate the privacy of someone, 50 years from now or something. So that's nice.
Is that always true?
Essentially. Basically, you can, in theory, like asymptotically, you can kind of choose, do you want perfect zero knowledge and, no, I'm going to get this wrong. No, for succinctness, you're always going to need computational soundness. Well, anyway, yeah, let's just leave it as like every snark in existence, the way they're made zero knowledge makes it perfectly zero knowledge.
And so for this, so Fry, the way you discussed it, it sounds like the only reason you would do that is if you really cared about post-quantum, or is there a different reason you might?
So when you get way into the weeds, there are some other reasons. So involving what field your circuit is defined over. So certain computations sort of naturally want to work over some field or another. And if you use one of these two category discrete log, or that field kind of has to come with a nice elliptic curve that kind of matches the field in some sense. Whereas this IOP-based stuff is just based on hashing, so you don't get field size restrictions from that, but you get field size restrictions from other things, like Fry needs FFTs, so that creates other restrictions on the field size. So way in the weeds of how these work, there are some other reasons you might want one or the other, further complicating the comparison between all the snarks out there. Yeah. Other questions? Okay, so now you sort of know the full taxonomy of snarks. We've roughly had 3 classes of polynomial IOPs, 4 classes of polynomial commitments. Of course, in each class there are multiple. So you're talking something like, even if there were only 1 in each class, that's already like 12 snarks, and there's more, and so there's like this combinatorial explosion. Let me make it even worse for you. So Tim, this is your question. Oh, sorry. My next slide is the answer to your question. So I want to run through the taxonomy of some of these kind of 12 possibilities and tie them to like the name of the systems people are really using. Okay, so the first class was sort of this exception class that wasn't quite based on polynomial IOPs with polynomial commitments, but if you squint, it's very similar. So the most popular snark in this class is now due to grow 16 because it really has the shortest proofs, just like 3 group elements. And the downsides here, Tim mentioned in a question, the trusted setup for this snark is circuit specific. So you change the circuit, you need a brand new trusted setup. It's not post-quantum, and the prover, I would characterize as pretty slow and space intensive. Okay, but the verifier is like really fast, and the proofs are really short. Okay, so there was interesting progress a few years ago that kind of, the big benefit was to turn the circuit-specific trusted setup into a universal one. So all that matters there is how big the circuit is, not like the specifics of its wiring. And so that's the big benefit, and so the main examples here are Marlin and Planck, and people are using these a whole lot today. The proofs are bigger. The prover is slower than the already, I called slow proof of grow 16. There is a counterpoint, which is the snarks that are truly based on polynomial IOPs, so everything that I'm going to describe but the top category, they can kind of use more general circuits. So you might wind up in a situation where, like for a given circuit size, like the Planck prover is significantly slower than grow 16, but you can apply the Planck prover to a smaller circuit. And so like slower prover applied to smaller circuit turns out in some cases to be faster than faster prover applied to bigger circuit. Things are complicated to compare. Okay, the next category, now moving to the transparent snarks, are take any multi-prover interactive proof or interactive proof, and combine it with one of the fast prover polynomial commitment schemes, which of course tend to have bigger proofs. These things, tend to always be intention prover cost and verifier cost. And the benefit of this, other than transparency and plausible post-quantum security, is going to be this is how you get the fastest prover in the literature. But people aren't using these today because the proofs are pretty big. And verification costs are very important in the things people are using these snarks for today. And the final category is like, it doesn't really matter what polynomial IOP you use, but if you use the Frye polynomial commitment, you're going to get the shortest proofs among plausibly post-quantum snarks. It'd be transparent too. And the downside is, the prover is pretty slow and the proofs are still fairly large. Like lambda, that's the security parameter, times log squared, is bigger than log, is bigger than constant, in some cases by significant factors, and I'll say more about that later. Okay, so that's the world of snarks. Yep.
So like if you imagine a world like not on blockchains, but like where your phone is like sending a snark to like a server, you imagine something like scenario theory is the most useful, where your phone can like prove the thing very quickly and like the server doesn't care how large the proof size is.
Yeah, and then you might want to choose a snark that people aren't really using today. Yeah. Okay, and then finally to get to Tim's question, so this is sort of ongoing work, so I don't have a specific result to tell you, so I'm just going to say it's what I consider a very promising approach to try to resolve the tension between prover time and verifier time. And it's not even a new idea, it's like it's very simple. It's known, but the devil's in the details of like, will it actually concretely be nice? So the idea is to take a fast prover, but kind of big proofs, maybe slow verifier snark, and compose it, I'll say in a moment what that means, with a small proof snark. So what this means is the prover, like in its own head, is going to use the fast prover snark to compute a proof, but it's going to be a pretty big proof. It's not going to want to send that proof to the verifier. Instead, it's going to use the small proof snark to prove that it knows the big proof, and send that proof to the verifier. So that proof is small and can be verified quickly. But as long as the big proof snark, I say it's big proof, that's sort of a relative statement. As long as the verifier of the big proof snark is like sublinear in the size of the original statement being proven, right? Like, computing the small proof what you're doing is you're turning this verifier into a circuit and applying the small proof snark to that circuit. So as long as this verifier is work-saving, right, that circuit is going to be smaller than the original circuit that the fast prover was applied to. This might be hard to grok online, but it's, in a sentence, in principle what this does is it makes the prover time dominated by the fast prover time, and the verification cost dominated by the small proof. So you get the best of both worlds.
Like maybe concrete parameters would help, right? So like fast proof or big proof, that could be like linear time proof versus square root proof size or something. Or square root like verification time or something like this, right? And then meanwhile, maybe the small proof, slow proof, or maybe that's a quadratic proving time, but you're invoking it on the sort of square root size proof, so that's just another linear term.
Yeah.
Right?
Yeah, so that's exactly it, except in practice, quadratic prover would not be that bad. It'd be like quasi-linear prover with just like gross constant and log factors. But square root is exactly right. So like the fast prover big proof, those snarks really do have square root size proofs. So like quasi-linear in square roots is still smaller than linear in. Yeah, the reason why this is still ongoing work is because doing this requires taking the verifier, the first snark, writing it down as a circuit, and then applying the prover of the second snark to that circuit. And that's just like a nasty thing to do. People are doing things like this all over the place, but I mean, my guess is just the groups doing that are just not very familiar with the snarks with the fastest prover. So I think that this very simple, just one composition of two snarks actually is going to wind up yielding very soon snarks with very nice cost profiles. They're not going to literally dominate on every axis, but I just think there'll be very nice profiles that might be attractive even in the rollup context. Yeah.
So maybe lower bound can't get
So people have, like very recently there was a nice workout that sort of, there are lower bounds with caveats. So you can sort of prove that like without using certain kinds of cryptography, you can't hope for constant proof size. You know, you can prove things about like the kind of cryptographic assumptions you need to base your snark on. I don't think we have, I mean, asymptotically speaking, the snarks we do have are really good. Like, you know, we have snarks where the prover runs in linear time. Can't hope to do better. We have snarks where the verifier runs in, you know, constant time, but there's an SRS, or logarithmic time, but there's no SRS. So the lower bound you could hope for is to say, like, you know, a transparent snark can't do better than logarithmic time for the verifier, and I'm not aware of a result of that, but I don't, you know. Does that make?
It does, but I guess as stated, this could potentially do better than all of the things we listed before.
So, yeah. So if you don't care about like logarithmic factors and like practical performance, you don't need composition to get everything you could ever want. If you care about the difference between log and constant, so you really do care about, you know, for the verifier, yeah, I actually don't know. Yeah, I don't even know if composition is going to get you there without a trusted setup. So I mean for this slide to be really a statement where you care about log factors and constants and concrete performance. And yeah, people are composing snarks today, but they're not using MIP and IP-based snarks that have the fastest prover in that composition. And I think essentially if they did, you'd get like new cost profiles that would be very attractive. Yeah.
And then how does the transparency and post-quantum security compose if you were to do this?
Great. So if either one of the constituent snarks is not transparent, the result won't be transparent. If either is not post-quantum, the result won't be post-quantum. If they both are, then transparency will be preserved, and post-quantum is sort of heuristically preserved, but that's not a formal statement. So like plausibility is going to be preserved, I think is fair to say.
And that's because plausibility is an informal term.
Yeah.
Okay.
Means like I would be surprised if you came up with a non-contrived example anytime soon that broke that, you know, where they're both independently post-quantum and you compose them and you can show the result is not post-quantum. I'm not an expert on formal post-quantum security proofs, but if you came to me tomorrow and said, here are two natural snarks that are both post-quantum, but their composition isn't, I'd be like, wow. Okay. By the way, when you compose known transparent snarks today, the security is like even classically is going to be heuristic. This is in the weeds of crypto, but like without the composition, you could unconditionally prove them secure in something called the random oracle model, which practitioners are quite comfortable with. But if you want to compose them, you're going to lose security in the random oracle model. So security is already going to be heuristic. Anyway, and I'm like very comfortable with that in practice, and I think all practitioners are. I mean, they're out there composing snarks today. So yeah, this whole plausibility with post-quantum is sort of no worse than the situation even with classical security and composition.
Is there easy intuition for why composition can mess up random oracle-based security? Or?
Yeah, so you have to represent the verifier as a circuit to then apply the next snark to. So, you know, in practice, the random oracle gets replaced with a cryptographic hash function. So the circuits have to compute the cryptographic hash function, like in the circuit. Cool. Okay. So I really was hoping to be able to come here and be like, look at my exciting new Snark, but I couldn't. So I'm just going to say I really hope that this leads to something. We'll see. Okay, so now we get to the final part of the talk. Looks like I have 30 minutes. Is that right, Tim?
Yeah.
Okay, rollups. Okay, so let me tell you what the context is for rollups and then how they work. So the idea is that public blockchains should be verifiable by weak nodes. You hear from, sort of the Bitcoin community, they'll take this to an extreme. They'll say if you're not running your own node, you just can't trust anything. So you want sort of verifying the blockchain to be doable by, certainly a laptop, maybe even a Raspberry Pi if you talk to, the really people who are extreme about this. A less extreme view is like if you need an Amazon server to run an Ethereum node, like you can't call Ethereum decentralized at that point. So we ideally want it to be possible for like weak devices to verify, that all transactions that have been processed by the blockchain to date are valid, right? Something like that. Okay, so there are two costs to running any blockchain node. The first is that they have to do computation to validate transactions. And in a little more detail, like for basic transfers and swaps and things, I think this computation is mainly just like checking digital signatures and making sure people don't overspend their accounts. But in general, on Ethereum smart contracts, the nodes might have to execute arbitrary EVM bytecode, and just a little more information about that if you're not familiar. So smart contracts in Ethereum are typically written, I believe, in Solidity. It's a high-level language, and then compiled to something called Ethereum Virtual Machine Bytecode, EVM bytecode, and the Ethereum nodes execute that bytecode. So, in principle, these smart contracts can do like arbitrary computation, so the nodes kind of have to be prepared to do arbitrary computation. But then, I think my understanding is a lot of the volume on Ethereum is just people sending each other money and stuff, and that's very simple transactions, not doing any crazy computation inside them. So in addition to the computation the nodes have to do, they have to store all the data that live on chain, with some caveats about, light clients and full nodes, and I myself am not super well versed in those differences. But conceptually, yeah, you've got computation and you've got storage. Those are the two costs. Okay, so yeah, let me just call like the data stored on chain like the state of the world, and for simplicity, you can just think of them as all Ethereum account balances, just if you want to make things concrete. Okay, so the very first idea of a rollup is just to treat the blockchain, or really the blockchain nodes, as computationally weak verifiers, and the rollup service as an untrusted prover. And this idea alone can save the verifier's work. So like rather than checking the digital signatures on a ton of transactions directly, you could imagine like some proof gets posted to the blockchain that all the digital signatures are correct, and then the verifier just like has to trust the proof and not check each one individually. So this is great. This will save the blockchain nodes work, but it doesn't directly, reduce the amount of data they have to store. Yep.
So if you can compress all the witnesses, probably like you can get rid of all the signatures on chain.
Yeah. So we're going to get to that as the second idea, I think.
Yeah. Okay. Yeah. I mean, that's some storage to me, right?
You're saying like don't even, instead of putting digital signatures with each transaction, put a proof of knowledge of a digital signature with each transaction.
Yeah, like if you have like one proof that you know signatures for like n transactions in a block that you've saved.
Great.
Something, right?
Yeah, so true. And I think that's another way of phrasing what I'm going to call the second idea. If you disagree, let me know and we'll talk more. Okay. Oh, by the way, like from now on, in case you haven't seen this terminology before, we're going to call the blockchain, like Ethereum, we're going to call that an L1, or the chain. And the rollup, we're going to call that L2, layer 2. Okay. So here's the second idea for rollups. This is to try to address the storage issue. And again, I think Joe just said this more or less. So we're not going to store the state of the world on chain. We're only going to store a cryptographic commitment to it. And you can think of this as often just like a single hash value, 256 bytes or something. So the binding nature of the commitment scheme will now ensure that once the commitment is on chain and everyone agrees on it, no one can alter the data that's committed to. So if someone comes and says, look, here's like a piece of data that's consistent with this commitment, and like here's the authenticating information that kind of establishes this consistency claim, like binding, the cryptography is ensuring that like their claim is true, and indeed like this is the data that was committed to by the on-chain commitment. So the key conceptual consequences of this is you no longer need to rely on the consensus mechanism of the blockchain to ensure that no one is messing with the data that the blockchain is really representing. Like as soon as there's a cryptographic commitment to the data on chain, like the binding nature of the commitment scheme means no one can go and alter the data. Okay. This raises the issue of now the data is only committed to, it's not just like stored on chain. So you can ask like, well, what if someone in the future needs to access some of the data that used to be on chain and now it's only committed to? This is referred to as data availability issue. And there's sort of two approaches people are pursuing to this. I guess it's actually, my understanding is a rich design space, but at a high level, the two approaches are like store it on chain anyway, or use economic incentives to get off-chain entities to store the data and make it available. So as far as storing it on chain anyway, it can live in cheaper storage called call data. This is like the Ethereum terminology, which my understanding is only stored by full nodes. There are definitely people who know more about this than I do. And moreover, Ethereum is considering changes to the protocol itself to make this sort of semi-on-chain option more scalable. So I know they're considering letting call data expire after a year and then sort of move to kind of the second option for kind of stale call data. If they implement sharding, which is going to happen sometime after the merge, it's kind of late in the game plan, that will increase the amount of on-chain storage. It'll do something like, I'm probably going to say this wrong, but there's something like multiple sort of related but blockchains getting stored out there. So each shard is sort of kind of like its own chain. I shouldn't have said anything because I'm probably saying it wrong. Anyway, it's going to increase the amount of on-chain storage. But if we're going to stick with this on-chain option, it will sort of put an upper bound on the possible benefits of rollups, because no matter how fast the verifier is for verifying the proofs, the dominant cost will just be like storing all this stuff on chain that is like not actually part of the proof. Right? It's just the data that's kind of committed to, has nothing to do with how efficiently the proofs are verified. Yeah.
Guys, like if I'm I don't know what the right term is, like a very minor user of Ethereum, can I feasibly just store like, I don't know, I'm interested in my own account balance, maybe like 1 or 2 smart contracts, or can I just like store that information myself, or am I going to have problems if I don't know some like local state when I try and spend my money or interact with these?
So I think if you send money to someone else, no, that might be okay.
I can talk more about this thing after, but there's like a couple of complexities that, basically like you can only rely on some random server to give you the data and sort of do verbal proofs and stuff to prove that it's okay, but even like receiving a transaction from somebody else, like if you want to verify the transaction, you need to know something about their state, you need to know their transaction counter, and so it's a bit tricky to validate anything if you don't really have like all the state. You either need all the state or you need to talk to someone that has all the state to prove stuff for you.
So even like just for you to send me money, you and I.
Not that you can do. You can send out money.
Just receiving money is more complicated.
Like verifying that someone gives you a transaction is actually valid before it appears on chain. But yeah, we should talk more about this though.
I see.
Okay. And it's a great question, and yeah, this roll-up part of the talk, I did my best to become well-versed in the whole idea of roll-ups, but this whole data availability stuff is not directly related to snarks, so keep that in mind. Let's put the two ideas together. Sort of the first one was about saving computation. The second one was about keeping less data on chain, or keeping it in call data instead of in the more expensive parts of on-chain storage. So a first attempt at how a rollup would actually work is sort of at all time, the L1 is going to store a commitment to the state of the world. That's like all of the data that used to live on chain. And the rollup will like take a batch of transactions and sort of, apply it to the current state of the world to get an updated state of the world, and then post a commitment to that updated state on the L1. And the problem is just how does the L1 know that the new commitment is correct? And basically the snark is going to prove that. So the rollup will also post to L1 a proof that sort of the updated commitment followed by applying a series of valid transactions to the old state of the world, and everything was valid, and it produced, the new state of the world produced this new commitment. And then note that the proof is the snark proof will be verified on chain. So like every blockchain node in the world will have to run the snark verifier. Okay.
So just to quick, so the transactions executed are part of the witness? Is that correct?
Yes. As is any authentication information, like Merkle authentication pass for any like pieces of data, that the transactions need to know to be applied.
Well, in particular, you're not focusing on the current paradigm where transaction descriptions are posted as call data. You're actually thinking maybe that's off-chain too, right?
Potentially, yeah.
Or like you're agnostic to that.
Yeah.
Okay.
Yeah, and you can run into situations where like if multiple transactions in batch hit the same account, then you only need to provide authentication information kind of once for, they're all hitting the same leaf of the Merkle tree, so you only have to do one lookup to the, initial account balance at the start state of the world. So you get savings. So like the bigger these batches are, so kind of the more that happens, and so you get extra savings because, certain accounts might be hit many times. So there are incentives to make the batches big beyond the fact that, we'll get into the main incentive to make batches big soon. Okay, so if everyone is sort of clear enough on how rollups work and what they're accomplishing, we can talk about their performance. Anyone want to ask other questions? Not too bad on time. I'm only slightly worried.
Sorry to go back,
Yeah.
but so is it, say that you wanted this property that you and I can trade money without knowing the entire state.
Mm-hmm.
I don't know a lot about Zcash, but presumably that's feasible to do on Zcash because no one's supposed to know the entire state. Anyway, is it
So I'm trying to think of this in my head. To provide authentication information for even just you and I, our accounts, there is information about other, not people you need to know, or it's not, it's really, you got this big hash tree. I haven't told you what Merkle tree is, but it's takes all the account balances and it, pairs them up and hashes them, and then pairs those up and hashes them. And the authentication information is all of the hash values on a path from your account leaf to the root and my account leaf to the root. So you need to know more than just that you have X Ethereum and I have Y Ethereum. It gets pretty hard to not know the state of.
And is that is Zcash doing something fundamentally different than that, or that's just also true in Zcash?
Joe, do you want to?
Yes, I think the difference is in Zcash, the definition of a transaction is the proof that a transaction is valid relative to some kind of state snapshot. Because the whole thing's wrapped in the snark. And in Ethereum, people think of a transaction as just this signed statement, and then to verify that, you need to go check it against the state. But you could sort of expand the notion of a transaction in Ethereum to also include Merkle paths that prove that the signed parts of the transaction are actually what's committed at that point in state. So it's you could redefine what you mean by Ethereum transaction a little bit to make it as verifiable as a Zcash transaction. You just have to add some extra stuff that people don't normally do because it's kind of assumed that everyone has the state stored anyway.
And just because Zcash is, zero knowledge, private, whatever, doesn't mean that necessarily that people don't need to store a lot of state. It's just the state isn't leaking anything about anyone's data.
I see. Okay, yeah.
And I'm not saying that people in Zcash do have to store a lot of state. I have, but it doesn't inherently mean that they. Yeah.
Well, yeah. In practice, they do because most of the Zcash transactions are not. They support non-zero knowledge transactions, which are just the same as anything else. But if you forked Zcash and had only shielded transactions, then like the amount of state you can store would be like a lot smaller.
Okay, so let's talk about rollup performance and how we would even measure that. Okay, so as something of an outside, like I'm an expert on snarks, but I'm not specifically rollup. So as an outsider to the space, it can be a little challenging to sort of understand, how people are measuring performance and kind of the states of various projects that are, they're very actively developing their capabilities. So tracking it can be difficult. So I'll give you an example of just some language that I think can be confusing if you haven't seen it before. So here's a proof of a tweet of Stark where they said we had 3,000 transactions per second, all 300,000 transactions in one proof, and it took us 6 minutes 3 seconds. So I don't know. Does anyone want to suggest what is a natural interpretation for that, like what that means? So what does 3,000 transactions per second and 6 minutes total mean?
They produce a proof in 6 minutes and 3 seconds that works for 300,000 transactions.
Yeah, so that's what I thought as I was trying to kind of understand the space. Turns out that would be a little fast. Like here's another example. This one from ZK Sync. They're talking about 20,000 transactions per second, so that's even faster than 3,000 transactions per second. As far as I can tell, so this is not talking about proof generation. So there's a difference between latency and throughput. So this becomes very natural kind of once I tell you what I'm pretty sure the rollup companies are thinking, but if you haven't seen it before, it's not so natural. I think so latency refers to the delay between a transaction posting to L2 and a proof capturing it hitting L1. And this is determined by two things. So like the time to compute that proof. But also, like, if your volume on L2 isn't that high, you're going to have to wait around until you have enough transactions that you're, then comfortable generating a proof and posting that to L1. Otherwise, you're going to have too many proofs on L1. Yeah.
And if your volume is too high, you have like some congestion issue, which also add to latency, right?
If your volume's too high. Yeah. I don't even know what you do, sort of, if your volume is way too high, like how you would keep up.
Yeah. Maybe it's just like queuing theory, like it sort of fills up and empties.
Yeah, over time.
But it could add a lot of like expected latency.
Yeah, so we maybe want to actually discuss this after we get to the other notion of performance, which is throughput, which is probably exactly what you have to think about with transaction volume. Okay, so throughput is the number of L2 transactions that can be processed in a given amount of time. And this is what I think the tweets I just put up are really talking about when they talk about transactions per second. And as I'm going to explain, technically this has nothing at all to do with prover time. So this is what I'm pretty sure they have in mind. So suppose one can upload a proof capturing X transactions, and it takes Y seconds to upload the proof. So forget about how long it takes to compute the proof. It's once you have it, it takes Y seconds to upload. So you can do something called pipelining. So what's going to happen is, every Y seconds, you're going to have collected a batch in the last Y seconds. You ship it off to the prover to start chewing on. And at the same time, some proof is going to have just finished being proved. You now have this new proof. You start uploading that to the L1. Okay. So kind of in steady state, this is getting kind of X transactions are kind of getting proved to the L1 every Y seconds. Okay. But it says absolutely nothing about latency. Like the prover could have taken a year. Just after a year, this pipelining has started posting to the L1, and from that point on, they're year-old kind of transactions, but they're getting a very high rate on L1. Throughput is what determines like blockchain scalability, meaning like how many transactions are kind of getting summarized on the chain every second. But latency demands will ultimately constrain the batch sizes. Like people aren't going to wait a year, just as an extreme example. And I think, I find when some of these rollup projects are talking about their performance, they know throughput is blockchain scalability. That's what we care about. So they'll talk. It's very natural. That's what they care about. They talk about throughput, but there's just no mention of latency at all, and that can be very confusing when you just see these things without that context. So this past week, I've been trying to learn about this stuff, and I had to puzzle this out. So hopefully, I'm saying this correctly. Yeah.
So like on the front end side, if you have like a prover for like, or like if you like there's a circuit for like the first like 10 transactions, can you like pipeline that and like add on like new transactions to the circuit? Or you have to like start all over again when you're like adding new transactions.
Yeah. So if we were talking about this, if you have a certain kind of proof system that supports a functionality called incrementally verifiable computation, you can do something like this where you can kind of prove a bunch of transactions and then in the prover's head, right? And then like more transactions come in and it kind of updates the proof to incorporate them, and then and kind of whenever it's ready, you can kind of stop and post the running proof to the blockchain. But as far as I know, the current blockchain projects are not supporting that functionality. Does that make sense?
Yeah.
But I mean, we know how, like there's a lot of interest in that functionality, like they could be supporting it. There are protocols known that support incrementally verifiable computation. Yeah, I do want to mention some counterpoints to this focus on latency, which is alternatives to these validity rollups do have high latency. So optimistic rollups, my understanding is right now they're sort of waiting around 7 days, giving people a chance to identify fraud. So you don't really get finality on L1 for a week. The non-blockchain solutions like Visa, it looks like your transaction went through right away, but it takes like 48 hours or something to settle. So people are tolerating pretty high latencies now. In some contexts, they don't mind, and even with the rollups, it might not be the end user that's taking on any risk of latency. It could be that a centralized exchange is the one interacting with the rollup, and they're going to promise users, finality, and if something goes wrong, it's the exchange that's going to be out a whole bunch of money or something like that. So, if there is high latency, people might tolerate a really high amount of latency in certain contexts anyway. Yeah.
So can we close the loop on the tweets? Like say
Yeah.
the 3,000 one? Just
Yeah, sure.
I want to make sure I get the point. So are you saying that so take the one on the left. So is it implication here that, so 3,000 per second is what like the L2 infrastructure could handle, presumably. Are they claiming that actually if L2 throughput was saturated, they would be able to generate proofs sufficiently quickly to keep up with that?
I think that's right. So I emailed Starkware about this and some other things, which I'll get to. And my understanding of what they told me was that this is counting upload time. 6 minutes is upload time. I don't know how to explain. Actually, 300,000 over 300 seconds is 1,000, not 3,000. So I don't know about that. But yeah, so I think, so this is upload time is my understanding of what they said. And then I sort of have puzzled out this whole throughput thing as the reason that this makes sense to just count upload time and not prover time.
Because she's doing proving while it's doing the processing.
Right. And like, so I do not know how long the prover took here, but the idea is like that's going to determine latency, assuming there's enough volume anyway, that they're not waiting around for batches to fill. But this pipelining thing sort of means, and if you forget about latency, like sort of doesn't matter for throughput with this pipelining thing.
Right. I mean, it's like the failure mode would be like 1,000 transactions come in, you start generating a proof for it, and then in the meantime, let's say you only have one machine to generate proofs, which is supposed to be. Right, and then while you're generating a proof for the first 2,000 new transactions come in, right, and then you do a proof for them, but then 4,000 transactions come in while you're doing that proof. And it just kind of.
Yeah, you don't keep up.
Yeah, so that's what I'm saying. Like, is an implication of this that they're claiming they can keep up, I guess.
Yeah, and I guess so. I mean, they were tweeting about some sort of proof of concept, if you will, for Reddit. Reddit had like a competition for rollup projects. I don't know the details. So there's some context here of this tweet that I'm not getting into and don't necessarily know all the details of. And I will say, I have a slide that we're probably going to run out of time for, but various kinds of composition of snarks can help address some of these issues potentially, where So maybe I should just jump to that real fast.
Well, so one other question, so like prover time as a function of the number of transactions is a function of the batch size? Is it sublinear in the batch size? Or
Prover time?
superlinear, or-
Prover time?
Yeah.
I mean, you have to at least read all the transactions in the batch. So linear in the prover time can't possibly be sublinear in the.
Yeah, that's what we were trying to say. So I guess I mean like the computational cost per transaction, you could imagine that being decreasing in the batch size.
Yeah, that's not how it's increased. You know,
Because otherwise I'm confused. Otherwise it seems like you're going to have a limit on how big your batches could possibly be if you hope to keep up.
you might, yeah.
And that limit on batch size might be well less than the sort of throughput that the L2 infrastructure can handle.
If you have to keep up.
You see what I'm saying? Or-
So here, let's jump to something. Here is how you might use kind of proof composition to address some of these issues that you're raising, I think. So imagine you had, I'm calling these sub-blocks, but you could think of them as just multiple different blocks. Okay. So block 1 comes in, you ship it off to the prover to compute a proof in the new commitment. Okay. As soon as you have the new commitment, you can start processing a new block. You don't have to wait for the proof to be done to start working on the next block of batch is what of transactions. And
I think actually maybe I can rephrase my question in a better way. Right? So like, imagine if the prover time was like A plus BX, where X is the number of transactions, or something like that, where A is big and B is small.
Yeah.
So the hope would be that B is so small that actually you could keep up with the L2 infrastructure.
Okay.
And then the point is just you need the batch size big enough so that the per transaction prover cost is approaching B as opposed to being dominated by A.
So that's exactly right. But then the problem is that the Snarks people are using today, their prover time is like n log n, and so you're right. Like if you take the batch size big enough, you know, I mean it's super linear runtime for the per transaction prover time is getting worse, not better.
Yeah.
But while I have the slide up, like let me point out something that can help kind of improve latency, even if the provers are slow, is Snark Composition. So you could imagine sort of breaking the block up into the batch up into much smaller batches. Have the prover chew on each batch in parallel. Okay. Now, because they're small batches, if you were to post each of these proofs to the blockchain, that'd be no good. That's a lot of gas. Okay. So instead, you can aggregate the proofs, and this is very similar to the Snark composition thing I talked about for resolving the conflict, but the tension between prover and verifier time. So this proof is going to prove knowledge of these proofs, each of which would have convinced, like the rollup verifier to accept. Given the preceding.
So assuming that the transactions that are in these subblocks don't touch the same thing ever.
No, it's okay if they do. So like, this proof would establish that like pi2 would have convinced the verifier that commitment C2 followed from commitment C1 by applying some batch of transactions. And so the point, like you need to know to start chewing, the prover to start chewing on this batch needs to know C1 but does not need to know pi1. And it'll know C1 quickly because that's just like Merkle hashing. But pi1 is what takes like a long time to figure out.
So each of the sub-blocks gets like checkpoints on the state.
Yeah. And that lets you sort of, rather than waiting for the whole giant thing to fill up and then having like a super linear time prover chew on like a giant batch. So that's kind of bad for two reasons. And this is getting similar to IVC, and it's not exactly IVC with this incremental thing. You can get the provers going on smaller batches in parallel. I think this will improve some of these issues in practice, but there's a limit to it because representing the Snark verifiers as a circuit is going to be nasty, and that's going to mean that the number of subblocks really can't get that big. While I'm talking about this, it looks like I'm going to pick up where I left off. I'm going to finish this talk next time, but I might as well finish talking about this now. So several projects are doing this. ZK Sync has been doing this for a while, my understanding is. So they use Plonk. I saw a blog post from 2020 that said they were doing this with Plonk, so it's been a while. They were actually doing this initially, according to the blog post, not for latency reasons, but they were using a structured reference string that was just not that big. And so if the blocks got too big, their circuit would need to be too big. They just couldn't prove. So that is, Joe, I said I'd mentioned at least some issues with SRSs later. That's an example of one. They found a way around it, obviously. So just much more recently, Starkware and Polygon Zero are doing this with Fry-based snarks. I don't really know what the performance is. I think it'll buy them some, levels of speed ups due to the parallelism it's unlocking, is my guess. But like the Fry verifier, like I said, the proofs are pretty big. I think that the number of subblocks is going to have to not be super giant, because you're just going to the statement being proved to aggregate the proofs is just going to get real nasty. That's my guess. Yeah.
I had a question about parallelism. Aren't there techniques to generate proofs using parallelism, that go short of actually full recursion or aggregation,
Yeah. So a lot of proof systems can be parallelized. Most of these do a giant FFT, which is kind of nasty to parallelize. You can do it, but so this is kind of a way to sort of more automatically do the parallelization. And then the other thing is a lot of these snarks, when applied to big statements in a non-recursive fashion, very space intensive for the prover, and the prover will just, fall over because it's out of memory, unless it's on I know Starkware, at least old work, they were using terabytes of RAM. I don't know what they're doing now. So they're just basically gross cost to having giant blocks. So this can help those costs in various ways. N log n is nicer if n is smaller, because that log n factor is smaller. So yeah, you can get parallel speedups, and people are without doing this. Some are also talking about, I know Starkware's talking about now having an L3. So it's like these proofs are getting posted to L2, and then these proofs then get, pi is getting posted to L1. I don't know exactly the details of the benefits of that, rather than just kind of waiting around to post pi to L1. I guess having these on L2 is, I don't know. So these are things people are thinking about. So I think
there's going to be Web3 and L3.
Yeah, exactly. Web3 and L3. I think I've seen mention of L4, so I don't know why. I think if they want ZK, maybe there's a reason to go to L4. So yeah, the numbers will get bigger. I saw this as people talk about Web 5, but I think that was some kind of joke. I didn't get the details of. Okay, so I'll finish up the rest of this presentation next time, and then tell you some more technical details of how these polynomial IOPs and polynomial commitments are designed. But yeah, thanks for all your questions. It's really good that I ran out of time, because it means the questions were good. And yeah, I'll say more next week.